Alright, so today we're going over 3 general launch word problems from the homework, starting with page 66, number 22, and I think I might see if I have a darker marker for the rest of this. Number 22 says, a football is kicked at ground level with a speed of 18 meters per second at an angle of 35.0 degrees to the horizontal. How much later does it hit the ground? So here's the ground. I'm going to draw a vector representing the initial 18 meters per second, 35 degrees. This is the initial launch of the football. Okay? It's just what happens to the football right on takeoff. If this were in outer space, this football would keep on going, or any weightless environment, this football would just keep on going forever and ever in that direction at that speed. Because it's here on Earth, what happens right as soon as it leaves the ground? What starts affecting it?
Gravity.
Gravity. Gravity starts pulling it back down right away. But in that first split second, we're looking at this situation. It's going to go forward with an initial velocity of 18.0 meters per second cosine 35 degrees, and it's going to go upward with an initial velocity of 18.0 meters per second times the sine of 35 degrees. What do we assume about its horizontal velocity as it goes through the air? What do we assume about its horizontal part?
That's a constant.
That it's a constant. It's just going to keep going at whatever 18 times the cosine of 35 meters per second is for every second it's in the air.
Right.
The question here is just how much later does it hit the ground? How much later? What are they asking for there? Distance or time?
Time. Time.
Time. They're asking for time. How much later? This could have been done last unit on one-dimensional motion. Does the horizontal velocity have anything to do with how long it's in the air? Yes, no, maybe so?
The what? I'm sorry?
The horizontal velocity. Does that have anything to do with how long it's in the air? No. Only the vertical does. Remember, the big point of this is you can treat these things completely independently. You can treat them as if they've got nothing to do with each other. So this question could be rephrased, how long is anything in the air if it is thrown upward at 18.0 sine 35 degrees meters per second, bless you, from ground level. I'm not going to write that part, but the assumption is from ground level. So this is what this question is really asking. If you kick something at an 18.0 meters per second at a 35-degree angle, the time in the air is only going to depend on the vertical part. In real life, there's a big exception to that. Anyone know what that exception might be? Because is this thing really just moving straight up? No, it is. We can pretend it's just moving straight up at 18.0 meters per second times the sine of 35 degrees, but it is also doing this, so in real life the only exception is if it hits something. What if somebody catches it before it hits the ground? Then this won't be accurate. But we're assuming that doesn't happen. So this is the question we have to ask. Can they totally ignore the horizontal part on this one? All right, Diego, can you follow me over here so I can leave that one on the board? So I'm just going to pull out, I've got my two general launch equations, V initial cosine theta times time, and y equals y initial plus v initial sine theta times time minus 1/2 gt squared. I just said we can completely ignore the horizontal equation for this one. You kick something from ground level. At what height does that, what are we going to call that altitude? At what height does it start?
It starts at 0.
Starts at 0 meters.
Wouldn't it also end at 0 meters in that case?
Perfect, Tyler. It also ends at 0 meters because we're assuming it returns to the ground. Otherwise, we have no idea what's going on.
Right.
Plus its initial velocity of 18.0 meters per second times the sine of 35 degrees. Time in the air is what we're interested in, minus 1/2 9.80 meters per second squared times squared times t squared. And this t will give us the number of seconds in the air as it goes from 0 meters back to 0 meters. We're only dealing with the upward component of it, and that is gravity, which is the only thing pulling it down. So this is going to be 0 equals 18.0 sine 35 degrees t minus 4.9 t squared. Normally I like to keep track of the units, but I don't want to confuse things, and I want to make a different point right now. What type of equation is this?
This is...
Go back to algebra 2. Begins with a q, ends with a quadratic.
Quadratic.
Yeah, this is the quadratic equation. Do we have to pull out the quadratic formula for this particular one?
No, not really. I mean, if you keep up with your units, I mean, you don't really have to.
No, here's what we can do on this one. I've got a t here and a t squared. I can factor a t
Out of the equation.
Yep, out of both terms in the equation. Faisal, you remember that? Faisal. Vishal, excuse me, do you remember that from Algebra 2?
Yeah.
Doing that kind of stuff? And as long as what you have is equal to 0, you can set each factor equal to 0. This is going to give us two solutions. One of them is time equals 0 seconds. Is that solution correct?
No.
Is it the, well, actually I think I tricked you with that question, Tyler. Is that solution the one we want?
No.
But it is actually totally correct.
I mean, yeah.
Because when did the football leave the ground?
It left the ground at 0.
Right, so this equation is telling us the football left the ground at 0 seconds, but that's not the one we want. We wanted when it arrived back at the ground.
Mm-hmm.
This is telling us when the football was here.
Launch.
We want to know when it was there. So the other equation this gives me is 18.0 sine 35 degrees minus 4.9t equals 0, or 18.0 sine 35 degrees equals 4.9t, or time equals 18.0, sine 35 degrees over 4.9, and that will turn out to be in seconds.
2.10.
2.10 seconds, I'm trusting you on
Yeah.
that. And why did I label that S instead of T? I don't know.
Wait. Okay, 2.10.
Double check.
But from here, from my answer, I'd round it up to 2.11.
Well, because it's 2.107. So if you wanna round
2.107. Yeah, that would be 2.11, three significant figures.
it. Mhm.
Okay, thank you. So t equals 0 seconds is a valid solution, just doesn't tell us anything we didn't already know. That the football left the ground in 2 seconds. We could also now use this to find out how far it went by plugging back into our horizontal equation, but this problem didn't ask for that. Whole point to this one was you could ignore the horizontal part completely and just treat this as an object that went up at 18.0 times the sine of 35 degrees meters per second. Any questions on that one? Think you guys can handle that?
Yeah.
All right, let's go on to number 24. Follow me back over here, Diego. Okay, now number 24 says,
Level 1.
athlete executing a long jump leaves the ground at a 28-degree angle. So theta is 28.0 degrees. Got to keep track of the sig figs. And he travels 7.80 meters. I'm guessing they mean horizontally, because that's really all they care about with a long jump. What was his takeoff speed? If his speed were increased by just 5%, how much longer would the jump be? Okay, so our two equations, once again, for general launch are x equals v initial cosine theta times time, and y equals y initial plus v initial sine theta t minus 1/2 gt squared. Do we have enough information here to find it? Let's see. He leaves the ground at a 28-degree angle and travels 7.80 meters. We want to find out his takeoff speed. Do we have enough information to do that? Does that look obvious? We know 7.80, right?
Equals v initials cosine 28t.
Cosine 28 degrees t. What's the problem with that one?
You got two variables you don't know.
We have two unknowns. Do we know anything at all about the other equation?
Well, I
We
think
know that
we'd assumed that.
G equals 9.80,
Okay.
and that y initial equals 0.
What about y final?
And that y final is 0.
Okay, so our other equation is, our vertical one, excuse me, is 0 meters equals 0 meters. And when you're doing a long jump, they expect you're going to land at the same height that you took off from, right? 0 meters plus 0 meters plus v initial sine 28 degrees time minus 1/2 9.80 meters per second t squared. So we still have our two unknowns. Thing is, oh, what did I leave out?
T.
I left out t there. We have two unknowns. You guys remember a little rule from algebra that if you have two unknowns and two equations, you can always figure something. You can always substitute, that's right. What are we looking for?
We are looking for
Initial.
V initial. Okay, since we're looking for V initial, I think I want to get time by itself in this equation and substitute.
right.
So if I go to my horizontal launch equation and I say time equals 7.80 meters divided by V initial cosine 28 degrees. Have I solved for time correctly there? Okay. Now I'm going to put this in for time everywhere in this equation. Hope you guys remember your algebra and pre-calculus skills.
Yeah.
Especially those who were just learning your pre-calculus skills.
Or have just already learned.
Yeah. All right, Diego, follow me over here. This may take a whole board to do clearly. I forgot that I gave you one last night that required substitution. That was a little bit neat of me. Okay, so now I've got 0 meters equals 0 meters, because I'm plugging back into my vertical equation with what I substituted for my horizontal launch equation, plus V initial sine 28 degrees. Now instead of time, I'm writing 7.80 meters over V initial cosine 28 degrees. Correct? Does that look right? You double checking me, Michelle? I want to make sure I don't mess this up. Well, it's 9.80 meters per second squared. Then in place of time again, 7.80 meters over V initial cosine 28 degrees, whole thing squared. Well, the good news is we have one equation where the only thing we don't know is initial velocity. That means we should eventually be able to get to the answer. Eventually. May take a few steps.
Eventually.
I am going to go ahead and stop writing the units for a second, just so I can concentrate on the algebra and a little bit of trigonometry. I'm rewriting this term with v initial sine 28 as a fraction over 1 times 7.80 over v initial cosine 28 as a fraction. And all I'm gonna do on this term is take 1/2 of 9.80, which is 4.9. I believe that's for now times 7.8 over v initial cosine 28 degrees squared. You guys okay with that?
Yeah.
I'm multiplying two fractions. I have initial velocity in one denominator, in one numerator, and in the other denominator. What can I do?
Yeah.
Cross it out. It's the same thing in both. What is sine divided by cosine as long as the angles are the same?
Is tangent.
You should have known that, Diego, right away. Sine over cosine is tangent.
Tangent,
We've been doing that. So this is going to be 7.80 times the tangent of 28 degrees minus 4.9 times 7.8 over v initial cosine 28 degrees squared. We're getting there. Believe it or not. I don't like that this is negative and this is 0. What can I do about that? I don't like that.
You can move it over to the other side.
I can move it over to the other side. I can add this term to both sides, and that's going to give me 4.9 times 7.8 over v initial cosine 28 degrees squared equals 7.8 tangent 28 degrees, right?
Yes.
I'm going to divide both sides by 4.9. And I'm going to pause for a moment for anyone to ask me any questions about what I'm doing here. How's that look so far?
That looks good so far.
Tyler, you're biased. You've been watching me do stuff like this for over a year. You're more used to it. Diego, Vishal, how's that look?
Good.
All right. You know I hate putting in decimals early. I lose track of what I'm doing if I just put in decimals.
Oh yeah, you mentioned that last period.
Yeah, I'm just not a fan of that. All right, I'm going to start breaking this down a little bit now. If I have 7.8 squared over here and 7.8 over here, I can divide both sides by 7.8 and just get rid of that. Get rid of one of them.
Equals.
Are you guys comfortable with me doing that?
That's fine.
So the bottom of this is still squared. The numerator was 7.8 times 7.8, and I had a 7.8 over here. Divide both sides by 7.8. And we're good. I think I'm ready to cross multiply. There's probably a faster way to do this, but I'm trying to show every step clearly. You guys okay with me cross multiplying here?
Yep.
All right. As I cross multiply, I'm going to distribute this exponent to both of my factors in these parentheses. So that gives me v initial squared
Cosine
cosine 28 degrees squared times the tangent of 28 degrees equals 7.8 times 4.9. So there's some more I could do with this. Basically reinventing something. You guys remember how tangent is sine over cosine?
Mm-hmm.
So if I have cosine squared 28 degrees over 1 times sine 28 over cosine 28, I can cross out one of those cosines, right? But just one of them. So V initial squared is going to wind up equaling 7.8 times 4.9 over sine 28 cosine 28. This was the long way to do this. I'm reinventing a range equation that I'm going to show you guys on Monday. There is a shorter equation for this, but I wanted you guys to think about this one first. That's part of the problem with you guys having a math teacher for your physics class. So what do you get for your V initial on this?
Okay, 92.2. That's what my thing says.
You get 92.2 meters per second. Did you take the square root yet?
Oh,
All right. Not many people, not many long jumpers hit a speed of 92 meters per second before they take off. That's a little quick.
9.60.
That seems more
Oh, yeah.
reasonable.
9.60.
9.6, third significant digit is?
0. 2. So
Okay, 0. Excellent. Meters per second. This was the long way to do it. I am going to give you a range equation on Monday, but I'm going to use this example to help show you guys where it comes from. Okay? I like to do that every once in a while. When, at the very beginning, did it look like you had enough information to solve this?
No.
No. But remember, if you got 2 unknowns and 2 equations, you can definitely figure out what's going on.
Substitution.
Substitution. In math, of course, sometimes you don't have any solutions from that. You get parallel lines, for example, but in this case, there was a solution. That's his V initial. This was the answer to question A, right?
yeah.
There was a question B. Follow me back over here. And question B said, if this speed were increased by just 5%, how much longer would his jump be? Okay?
So you just calculated 5% of that and that.
Yeah. Algebra 2 or Algebra 1 review, what's the fastest way to get 5% of that? What do you multiply by?
1.05.
Very good. So first, 5% bigger, 5% more means 1.05 times the initial. Got a question, Diego?
No.
We have the answer?
Yeah.
Okay, so 1.05 times 9.60 meters per second. What's that get you?
0.48.
10 point,
No. 0.48.
10.1.
10.1.
10.1 meters per second. Okay, so how do we find out how much further he goes?
Plug that into.
Review our 2 equations here. We've got x equals v initial cosine theta times time. We've got y equals y initial plus v initial sine theta time minus 1/2 gt squared. If we plug it into here, we figure he's still leaping at a 28-degree angle, right?
Right.
They didn't change that.
But his time and distance would change.
Yeah, and we don't know the time.
Still.
Do we have enough information to find his time in the air, though?
Yeah.
He starts at 0, he lands at 0. We know his new v initial, we know his angle, solve for time. Think we can do that?
Yeah.
All right?
Why not?
I agree, why not? 0 meters equals 0 meters plus 10.1 meters per second sine of 28 degrees times time we're interested in minus 1/2 9.80 meters per second squared time squared. Multiplied times time squared. I'll do this algebra a little bit more quickly over here on this board. And when I give you guys the range equation, you'll be very annoyed that I did this the long way today. But I want you guys to get this part down, understand how this all plays together, how these 2 work independently. Okay, so once again I'm going to get 0 equals 10.1 sine 28 degrees t minus 4.9 t squared. Again, I'm going to factor out a t. Leaving me with my two solutions of time equals 0, that's when he took off, and 10.1 sine 28 degrees minus 4.9 t equals 0, which will tell me when he landed, I hope. And similar to last time, when I'm done rearranging, I'm going to get 10.1 sine 28 degrees divided by 4.9, and what's that going to be about?
Okay.
I'll let you guys handle the button pushing.
Around 0.97.
What did we get for the last one? What was his time in the air with the last problem? Did we find out? Do you remember?
2 seconds, I think.
It was 2 seconds?
2.1.
Yeah, 2.1. That doesn't make sense. I don't think he'd go down to.
I'm not sure how.
Sine 30 would be 1/2. This should be around what did you get?
I said 0.97.
That actually makes sense for the math. 0.97 seconds. But is that going to get him going further? Because this is 0.97 seconds. So we've got, this is about 2, right? 10 over 4, this is about 10 over 5. And sine of 30 degrees would be 1/2, and 2 times 1/2 would be about 1, so that's right. But why is he in the air for less time now? Are we sure we had 2.1 seconds before about? Or no, we eliminated time from the last one. We never found how long he was in the air.
Yeah, we never did.
Bingo, we have no idea how long he was in the air last time. That's what I was brain farting on. Okay, thank you. Because we got time out of the equation and solved for initial velocity without time. So we never found that. Okay, thank you for helping me work that through. I got a little distracted by that, not knowing how much time it was in the first jump. But we have enough information now to go back to horizontal distance equals initial velocity cosine, in general, cosine theta times time. And specifically for this one, it's going to be x equals 10.1 meters per second times the cosine of 28 degrees times 0.97 seconds. So that should be about 10 meters, because this is close to 1 and that's close to 10. And then times the cosine of 28, cosine of 30 is about this should be about 8 point something meters? 8.6. What's the third significant digit?
5.
8.65 meters. That seems about right to me. So that was not a short problem. But that's our answer to B. And I will give you an equation. On Monday we'll talk about shorter ways to do this.
Did it say by how much faster he
Or by how much farther? Oh, good. Well, how was the question phrased? Good question. B said, if the speed were increased by just 5%, how much longer would the jump be?
So
Good,
subtract
good
that by.
So that this is not the answer yet.
Subtract that by 7.8.
Yep.
B.
So your answer would be, your change in length, delta x, would be 8.65 meters minus 7.80 meters, which is 0.850 meters. That's your answer to part B. Thank you. Thank you for catching me on that. Any questions on that one? That was a short, intuitive problem. Easy to guess what the answer would be, right?
Yeah.
And then 26. Okay, 26 is fun. This has some fun thought to it. All right, let's go back over here to this board. First part shouldn't be bad. Let's see if we can do this one without that range equation as well, because I want you guys to appreciate it. 26 says, a hunter aims directly at a target on the same level, 75.0 meters away. Here's the hunter.
Oh, that one.
Here's the target. You're 75.0 meters away.
The velocity would be 180 meters per second.
A, yep. If a bullet leaves the gun with an initial velocity of 180 meters per second. And this is horizontal, right?
Mm-hmm.
Okay, by how much will it miss the target? I guess they don't say how big the target is, so I'm guessing the target is like just a bullseye. That's what I have to presume reading this thing. If something's moving at an initial velocity of, if it's moving just any velocity of 180 meters per second, for one thing, this is the horizontal part, so we always treat that as constant. It's going 180 meters, next second it's going 180 meters. The horizontal part, I can't say this enough, assume this is what would happen if you flicked it in space. Okay? So it's just going to move like that. How long will this take to cover 75 meters? And how do we find that out?
0.42
So you just did 75.0 meters divided by 180 meters per second?
So what I did, it amounted to that, yeah.
Right. So if you divide the distance by the rate, you'll always get the time. And what'd you get for that?
0.42 seconds.
0.42 seconds. Okay. Any questions on that? All right. Here's how I want you guys to think about this when you have a time. How far does anything fall in 0.42 seconds? How do we find that out? Now we go to our y equals y initial minus 1/2 gt squared. Why do I not have a v initial sine theta t in there?
Because sine theta 0 is 0.
Excellent. Sine the theta, this is a horizontal launch, which is at a 0-degree angle, and the sine of 0 is 0. That's why your horizontal launch equations don't have that middle term sitting in them. All right, so this thing, let's call it, we're looking for y. Let's say it started at 0 meters, minus 1/2, 9.80 meters per second squared, times 0.42 seconds squared. And what are we going to get for y here?
What happened was I got negative 0.86 meters, which is by how much the gun missed the target.
They never actually say it's a bullet, but you got to assume. Just out of curiosity, out of 75 meters, how far down is less than 1 meter?
Not that much.
Yeah.
So you only need a really point.
Well,
1 degree higher, maybe.
I mean, if your target's more than 1 meter large, you're still going to hit it. Are you going to get a bullseye though?
No.
No. You'll hit one of the outer rings if it's more than 1 meter. Okay, so that is by how much you miss what you're aiming for. Now for the fun part. We don't want to miss though. We want to hit it. How are we going to figure that out? Is this still going to be a horizontal launch problem if you want to actually hit the target exactly?
No.
You have to hit it a little bit.
You're going to have to tilt it up at some angle, and once you tilt it up at an angle, we need those other equations. All right, follow me over here, Diego. And let's see what we've got. Okay, so now our equation, now we go back to part B to x equals v initial cosine theta t, y equals y initial plus v initial sine theta t minus 1/2 gt squared. What would we like our, well, okay, we're going to assume we're still starting from a height of 0 meters. If we're calling our initial height 0 meters, what would we also like our final height to be in order to hit this target?
Let's see.
We're calling where we start 0 meters.
We would like to be 0 again.
Boom, yep, we'd like it to be the exact same level. So if we call our starting height 0, we want to call our final height 0. Our V initial is still 180 meters per second. Can't really change that. Sine of theta we don't know.
Would it change? I think
Would the time in the air change? Yes, unfortunately it would. Our time in the air would change because it's covering a longer distance. It's, well, not probably by much, but we can't assume it's going to be in the air for the exact same amount of time. It's not it no longer is just dropping from that height.
Right.
It's going up some and then falling down some. So we don't know that time.
It's probably just not negligible enough. Or
Yeah, we can't quite ignore it. So we're going to have two unknowns, t and theta. Now, that means we're going to have to go back to this one. But we do know that the horizontal distance is still 75.0 meters. We do know the V initial is still 180 meters per second. We don't know the cosine of theta, we don't know time. So if I go to my other horizontal launch problem, I am again back to two unknowns, but two equations.
Oh yeah, just like how we did the last one.
So I did the last one. Now which one do I care about here, time or the angle?
Care about the angle.
Question asked for the angle, so I don't care about the time right now. So I'm going to solve for time. That's kind of the counterintuitive thing about this. You solve for the one you don't care about. I don't care about time, so I'm going to solve for time and say that it's
5.0 meters over 180 meters per second times cosine theta.
Yep, very good. And now I can put that into this horizontal launch, into that vertical, part of my general launch equations. And this is going to be, go back to this equation here. And now I'm looking at 0 meters equals 0 meters plus 180 meters per second sine theta. Instead of time, I'm going to write 75.0 meters divided by 180 meters per second cosine theta minus 1/2 g, gravity, times 75.0 meters divided by 180 meters per second cosine theta squared. Any questions on how I plugged that one in? You guys good with that?
Right.
I've really just got two terms here. I've got 0, 0, this term, this term. So this is going, it's going to turn into 0 times 180 times 75 over, I'm sorry, I left something out here, something important.
Sine.
Yeah. 180 sine theta over 1 times 75 over 180 cosine theta minus 4.9 1/2 g 75 over 180 cosine theta all squared. What happens to the 180 and the 180?
Cancel out.
What's sine over cosine?
Tangent.
Does everyone agree with Tyler on that?
Yeah.
Okay, so that's going to be 75 tangent theta minus 4.9 75 squared over 180 cosine theta squared.
You can move the negative term over by adding.
Yep, and that's going to be 4.9 over 180 cosine theta, whole thing squared. Forgot the 75 squared on the top. I'm leaving it as 75 squared for a reason. Equals 75 tangent theta. I've got 75 squared here and 75 here, so I divide both sides by 75 to get rid of that. And I'm going to multiply both sides by 180 cosine squared, so that's going to give me 4.9 times 75 equals 180 squared cosine squared theta tangent squared theta So this is going to get me 4.9 times 75 over 180 squared equals, what do we say happened with cosine squared tangents squared again?
Let's see.
It's cosine theta times cosine theta. That's the cosine squared over 1.
Oh, you get rid of one of the cosines while
Yep.
making the tangent sign.
So this becomes sine theta cosine theta. Now this part does get trickier going for the angle, because there's an identity here that I don't think you guys have learned yet.
Not even.
You have.
Oh, yeah.
You did this last year.
Mhm.
But you guys may not have learned yet that if you have sine theta cosine theta, it's the same thing as 2 sine. It's actually the same thing as 1/2 sine 2 theta.
Oh, yeah, the.
Double angle identities?
Yes.
Okay. Diego or Vishal, have you seen that before anywhere?
No.
Okay, so this is the key thing that you guys haven't learned, that the range equation makes a lot easier. Alright? With this, we can solve this. We're going to get down to sine 2 theta equals 2 times 4.9 times 75 over 180 squared. And we're going to pick up from there on Monday and talk about how the range equation works. Okay, we're not going to finish this one today because we're about to run out of time. Any questions on this? This was a lot of algebra today. You guys handle that all right?
Yep.
All right.
I was even able to recall the double angle.
You were able to recall the double angle. All right, Diego, why don't you cut it off there, and we'll pick up from there on Monday.